I am joined by my team members Rachel, Chase, and Helen, and we're going to be giving the presentation today. I am also joined by Kayla, Mohammed, and Ahmed, and they will be helping to answer questions at the end of the presentation. A brief overview of what we're going to go over today. We will restate our mission statement for the last time, and then we'll go into the solution of how we decided to uphold that mission statement, and then go into the requirements we had in place, and then go into our test plan and the results and how we upheld those requirements. And then we'll open the floor for some questions.
So the general premise of our project is that we want to make sure that a child will not get separated from their parent. In order to do this, we decided that we wanted to send alerts to both the child and the parent so that we can accomplish this. The holistic solution for what we have is a child wristlet locating device and a mobile application on the parent's phone. The device for the child is almost like a smartwatch motor, and then the mobile application will also send notifications to the parent to alert them.
So I'm going to tell you a little bit about the parent application. As Rachel was saying, the parent application will stay in communication with the child wristlet locator. And you can imagine on the right-hand side of the screen, you see the different areas indicated by different colors. The green is the safe zone, the orange is the warning zone, and the red is the danger zone. You can sort of imagine the parent with the phone right at the center of those circles, and you can imagine the child wandering about in between the other zones. And so, in order to be able to set the different zone parameters, how far away you want those zones to be, the parent application allows you to do that by selecting predetermined distances, and it will also tell you the distance that the parent is away from the child. And it allows this by taking in GPS coordinates from satellites, so it knows where its own location is, and it takes the GPS coordinates from the child's device over Bluetooth. It will then compare these two distances and then display the distance between them on this application. This application will also indicate what zone you are in, and it indicates this using different colored blocks. So right now on the application there's a red block which indicates that the child is in the danger zone. Lastly, if the parent is feeling a little bit anxious and thinking that the child is wandering a little bit too far away, the parent can send an alert to the child to get that child's attention.
On the child wristlet device side, it's comprised of the electronic housing, the band, the locking mechanism, the printed circuit board, and also the rechargeable battery. The rechargeable battery is located underneath the printed circuit board, which is also connected to a micro USB, which is waterproof. This allows for the battery to be rechargeable from the outside using the standard micro USB cord versus the non-standard Apple cord. So this rechargeable battery sends power to our printed circuit board, which is comprised of the microcontroller, which is located right here on the left-hand side. The GPS, which sends the child's current location to the parent application. The Bluetooth module, the vibration motor, and the programmable LED. The point of this printed circuit board is that the brain is the microcontroller, and that's where our program is stored to determine what data is being sent and received to the parent device. So about every second, the GPS location is sent to the parent device, and it's compared to the parent's location right here, and then the zone is calculated from the parent application and sent back to the microcontroller. Based on what zone that child is in, the safe zoning, meaning in that green circumference, the green LED on the circuit board will light up and there will be no vibration from the vibration motor. If the child wanders into the warning zone, the LED will then turn orange, indicating they're in the warning zone, and then there will be a pulse width modulation from the vibration motor at 50% duty cycle. So it's a milder vibration to the child. And then the danger zone, the LED will turn red, indicating that they're in the danger zone, and there will be 100% duty cycle, indicating that there is an intense vibration. Like Chase mentioned earlier, there will also have the capability of the alert button, at which no matter what zone the child is in, the LED will flash on and off on the device, as well as the motor turning on and off rapidly. So in addition, we had some extra time in our project, so we took it upon ourselves to implement a push button onto our device, basically resolving some of our battery issues, leaving the printed circuit board on too long. So what happens is we have a push button implemented, and when the push button is pressed, a blue LED turns on, which means it's searching for the Bluetooth module on the parent's phone.
All of the components that Helen just mentioned are on our PCB, which are in the electronic housing that you can see here, which is labeled A. And this housing is then put onto the band, which is B and C. So parts A and C are printed with rigid PLA, and the electronic housing is printed using the regular printer bots that we have just in the manufacturing lab. The fun part is that B and C, the band and the electronic, and the locking mechanism, are done using dual nozzle extruding. So that was done using the Flashforge Dreamer that we have in the back. We have flexible material going in one nozzle and rigid going in the other. This way we could do this in one print, so that we could make sure that the band was going to adhere to the locking mechanism in one component, as you see here.
Our requirements were determined from our client, Professor Will, and our advisor, Professor Johnson. So we have these specified requirements here that the device was intended for the child to wear and to receive alerts, that it must be capable of notifying both the parent and the child when defined distance parameters are disrupted. On the parent side, the parent must have an interface for which they can receive and send information to the child. On the child device, it must be tamper-proof, splash-proof, and durable. It must be capable of operating efficiently and charging quickly. And it also must be lightweight and comfortable for the child to wear onto their wrist. For our test plan, we had 3 variations: the electrical, the communication, and the mechanical. For our distance parameters alerts, we have a video here to show you that Rachel here in this video is wearing the device, and you can see she is close to the parent application on the phone, for which the LED is turning green, satisfies that they're in the safe zone. The LED is indicating the zone that they're in. So there's no vibration here because they're in the clear. So then Rachel's going to walk out of the safe zone and into the warning zone, for which the LED is going to turn orange. There's mild vibration. For sound purposes, there's no sound, so you'll have to take our word that the motor is on. But then she walks out into the danger zone and the LED turns red. Caleb then sends an alert from the mobile application, and the LED starts blinking, and also the vibration motor turns on and off rapidly. So this satisfies our distance parameters alert for our SDRD requirement of it must be able to send and receive alerts. For the mechanical vibration alerts test, what I did was I took a sample size of 5 non-biased Valpo students, and I put the child wristlet device onto them. I then randomly changed the different zones between the safe zone, the warning zone, the danger zone, and the alert mode, and had them identify which mode it was. This was very successful. All 5 of our students were able to determine which zone they were in efficiently.
Now I'd like to talk a little bit about the Bluetooth connectivity test that we performed. For the Bluetooth connectivity, there were 2 requirements. First, there was the speed at which they communicated, and second, there was the range over which they communicated. For the first requirement, the speed at which they communicated, we were able to use 2 videos one video recording the child wristlet locator, and the other video recording the parent application. We were able to sync those two videos and then have a timer with it to calculate the time between sending a message from the parent application and receiving it on the child's side. And the requirement was that the communication had to be less than a quarter of a second delay. We exceeded that by having it, on average, less than 1/10 of a second. For the range, we were able to, or the requirement was to be able to have the two devices communicate up to 125 feet. This is using Bluetooth, so Bluetooth isn't really known for being very long distance connectivity. We, in our search for a Bluetooth module, sought one that had a longer connectivity, and we were able to test it up to 470 feet. And that was, they were still connected. We ran out of room, so we're going to actually do some more connectivity tests to see how far the range can actually go.
Okay, so for the battery, there were two different requirements. One, it needed to be able to last up to 3 hours, and it needed to be able to charge quickly, and we determined that to be charging within 2 hours. So we did two tests to satisfy this. We took the battery and we ran our system completely, so full vibration motor, full zone difference, and full GPS running. And in order to do that, we went around downtown Valpo and had the GPS tracking our location, and every 30 minutes we would change the different, we would cycle through the zones, and so we'd go from green to yellow to orange to red, and then press the alerts to make sure the connectivity was working and the system was operating as we saw fit. And that proved that we had a battery life of about 3.5 hours, which is greater than what we wanted. And then we did another trial of that, which was just in Gellerson, to see if the GPS pulled a little bit more battery. It resulted in about the same time. The only difference in this test was we were standing still in Gellerson, and we were measuring the voltage across the battery terminals every 30 minutes. We still cycled through every 30 minutes of the different zones. That resulted in a similar battery life, so about 3 hours and 30 minutes, which completely exceeded our expectations. So moving on to the charging. This was a little different. Once that battery had been fully dissipated by our system, we decided to charge it using our micro USB cable that we made. This, we measured the battery terminals every 30 minutes for their voltage and recorded that. We repeated this test twice, and it turned out that we took a little bit longer than we really wanted to fully charge, about 2 hours and 45 minutes, which is about 45 minutes longer than we wanted. However, it is important to note that we fully dissipated the battery so that our system wouldn't work anymore, and then charged from there. This is not exactly what would happen in a real life situation. Let your phone completely run out before you plug it into the charger. And so if we take in account a difference of 30 minutes, that will get us much closer to the 2 hours that we were looking for. So moving on to the mechanical test. One of the requirements is that this device be tamper-proof. And in order to satisfy that, we locked the locking mechanism and then used a spring gauge, as you see here, which we attached to the band and pulled on it to what we felt was max capacity. We had the device in one hand and the end of the spring gauge in the other. And that resulted in about 11 pounds of force, which is roughly 44.4 newtons, which completely exceeds our desired 7 newtons of force. And a second part to this test, we wanted to see what would happen if it broke, where it broke, and what it would take to break it. So we clamped the device in a vise and then pulled on it and maxed out the spring gauge every single time. So we upped the force a little bit, put a Allen wrench through the band and just tugged with all body weight, and that took about 3 times before it finally broke. It's important to note where it did break, and where it broke was at the connection between the ratchet mechanism and the band, and this actually says that this is going to be a safe break for the child. So this this is an opposite print, but when it breaks, you'll be able to pull it down and take the device completely off, so it's completely safe for the child.
Another mechanical test that we had to do was to check the size and weight of the child device. Size-wise, we had to make sure that it could fit children between the ages of 3 and 8 with the 20th to 80th percentile. So we actually went online and found a bracelet sizing website. And for 3-year-olds on the 20th percentile, the general circumference that we wanted to be in was 5.5 inches. And then for 8-year-olds on the 80th percentile, it needed to be 6-inch circumference. And when we take our device and we tighten it as far as it'll go, we have a circumference of 4.7 inches. And then when we make it so that it's still locked but on the loosest setting, it'll be about 6.3 inch circumference. So because our range is greater than the desired range, we know that we have passed that test. To test the weight, what we did is we put the electronic housing, the locking mechanism, the band, the PCB, all of that, we put it on a scale. And our requirement was that we had to be under 7 ounces, and our final weight came out to be 2.8 ounces, so we were well under the required weight. Our last mechanical test that we had to do was the particles and water test, and the requirement that we had to be under was IP21 standard, which means that particles greater than 12.5 millimeters cannot get into the device, and it has to be splash proof from water being dropped on it from above. Luckily, last week we had some very rainy days. So what we did is we put the lid on the electronic housing. Well, we put a piece of paper on the inside and then taped off the lid to simulate the glue that we're going to have on the final product. And then we stuck it out in the rain for 5 minutes. So we have a video here. And we just let that sit out there. And once it was done for 5 minutes, we brought it back inside, took the lid off, and found that the piece of paper was dry. So this means that there will not be water on the inside of our electronic housing, and we do have a splash-proof case, which means our PCB will not get wet. To test the particles, to make sure that particles greater than 12.5 millimeters will not get inside the electronic housing, we measured the opening where the micro port will be, and that opening is 9 millimeters, so since that is less than the 12.5, particles greater than 12.5 cannot get in there.
So as you can see, we met many of our requirements, and we believe a project is never really finished. We would like to be able to look in the future, things that we would change, and things that we would like to continually to improve this project. One of it would be making the housing and the locking mechanism smaller, just so it's a little bit more comfortable for the child. And then in addition to that, we'd like to make the locking mechanism able to activate and deactivate using NFC capability. So that way the parent doesn't have to bring around a lock, a key for the lock, but they can just take their phone, bring it to the child device, lock it, unlock it, very simple. Another thing that we'd like to do would be upgrade the application, and we'd like to do this in a few fields. One would be to get the GPS coordinates more accurate. Currently we have it ranging in about 20 feet. It'll jump around, and the GPS says that it should, using Android Studio and Google API package, should be around 2 to 3 feet. So we'd like to do some more testing and figure out why we're not getting that. We would also like to have solar panel charging. We think it would be really nice to be able to make this project green, as well as to make the project overall more aesthetically pleasing for the child as well as the parent. So it doesn't look like the child doesn't feel like it's a tracking mechanism, but it's something that they can enjoy and wear.
So in summary, we restated our mission statement for you, and then went through our solution and how we're going to solve this problem, and then also went through some of our requirements and how we tested these and shared some of our results with you guys.
So I just want to take a second and thank everybody here for a great semester. It's been a heck of a time with these wonderful team members. We started from scratch with a basic idea, took it through various phases of a prototype, and made it a successful working senior design project. So I'm very proud of our team. I also like to give special thanks to our our advisor, Professor Reva Johnson, and our client, Professor Will, in addition to some very important faculty and professors such as Professor Blood, Professor White, and Professor Thomas for helping us with our project. So thank you all for a great semester, and now we'll open the floor up for some questions. Stephanie?
So I know you have like the green, orange, and red like at certain distances. Is there a way, is that like a set thing, or can like the user like, change it on the app, or is there like future things with that?
That's a great question. So Stephanie's question was is there a way to change the distances between the safe and the warning zone? Yes, there is. On our mobile application, we have two distance parameters that were identified from our client, 8 and 12, and then I think 16 and 20. So those will be changed. Blood's question was, what would be the easiest way to shrink it down? And that's a combination of the mechanical and electrical, so I'll let our CTOs take that question.
So one of the ways we can miniaturize the mechanical side of things would be first off with the locking mechanism. If we did go with an electronic NFC chip, that would take this whole part and pretty much flatten it. But then also with the electronic housing, the way that we have the PLA set up, it's the thinnest the wall can be right now without the wall starting to warp. But if we had more time and we could manufacture a different material that the wall could be made out of, then we could have the walls be thinner and a little bit more compressed.
And so to answer the question on the electrical housing side, currently our device is about this big for all the electronics. Some ways to reduce the size would be to have the button on the printed circuit board, as well as to have the micro USB on the printed circuit board. That may make it a little bit smaller. And otherwise, it's pretty compact the way it is. It is currently 1.25 inches by 1.25 inches. So we're pretty happy with the size overall for the electronic portion of it.
There's my Apple Watch for scale. So I think we did a pretty good job getting it scaled down. Professor George?
What units you're using right now, and how you're charging them? What's the system? What's the circuit charging them?
So Professor George's question was, what are the batteries and how are they being charged? So Mohammed is in charge of our batteries, so I'll let him answer that question.
Okay, so what we choose is a lithium battery, and we charge it by building a circuit, have two capacitors and one voltage regulator. So there is a capacitor for it's connected to the rest of the device, and another capacitor in the device itself. We have a voltage regulator also, because once we charge it, the charging voltage required is higher than what we required for our device. So we have a voltage regulator to reduce it down to 3.3. So if we have what's required for charging is 4.2 voltage, and the voltage regulator will be able to reduce it up to 3.3. And once we disconnect the charger, the battery will give us up to 3.7 voltage with full charge, and the voltage regulator also will be able to reduce to 3.3 again. The battery will reduce the voltage during time up to 3.2. Once it's 3.2, the device will die. But whatever between 3.2 and 4.2, always the output will be 3.3.
Professor Blood?
Are there any other markets you could use this device for?
That's an excellent question. So he wants to know whether or not there are other markets for our device. And we did do some research. At the beginning of the semester, we did have a sample test of where parents could use this. They were included but not limited to amusement parks, grocery stores. Our advisor would like to take it to the grocery store. And there was also a suggestion to go to daycares within the area, and maybe they even have the capability of hooking up multiple devices to one parent's phone. So that's kind of our scope of what we'd like to expand to.
Do you think you might be able to do other sorts of revenue beyond children though? That's what I was really trying to get at.
Ideally, we'd like to go to Disney or some Six Flags, some major corporation that kind of has a market for finding children. I mean, if you go to Disney, the way to track down children is very limited. They have those Disney vans where you can track which ride they go on, but not really an exact location of where they are. Are there any other questions? Thank you all for your time.